Hello guys, welcome back. This is our final video on theory for gas power cycles, and what we're gonna study today is the Brayton cycle. Brayton cycle is the ideal cycle for gas turbine engines, and it will be a little bit different from what we have studied so far. Let's start by saying that this cycle is an open cycle. Usually we have fresh air from the atmosphere drawn to the compressor. You increase its pressure and then you mix it in a combustion chamber with fuel. Once that you mix it in that in the same combustion chamber, you make combustion of that mixture will release a lot of energy. Gases will try to expand, and you expand in a turbine. Part of the work will go to the compressor, so the same turbine will power the compressor, and the rest will be delivered for its use. After the expansion, we have excess gases that go to the atmosphere. So these 2 points, 1 and 4, are pretty much the same pressure since it's atmospheric air. Each of these components is an open component, has mass flow crossing the boundary of this compressor, the combustion chamber, and the turbine. The way that we are going to idealize this is we're going to substitute this part by closing it, and we are going to use a heat exchanger constant pressure, and that will take care of these exhaust gases. So our ideal cycle will comprise of 4 cycles. One will be isentropic compression. Then we are going to change the combustor chamber to a heat exchanger, so we add heat addition at constant pressure. Then we have expansion in an isentropic turbine. And after that, we are going to reject heat in the heat exchanger, so we have a heat rejection at constant pressure again. Same as we have in the original cycle, part of the work of the turbine will go to the compressor, and the rest will go to the out as work net. We're going to discuss that we have 2 main purposes of this cycle. Let me just change our pointer, and one of them will be power generation, so in that I would like to have a highest network. And the second is aircraft engine. In that I will try to have the thrust high. So pretty much the compressor of the work of the turbine will go to the compressor, and the rest of the air, what I would like to value is the exit velocity. Okay. This is a typical gas turbine, and we can identify here the compressor. We can choose this as a compressor because we have a higher height in the first part. You can see that this height is much more than this one. So as the airflow goes in this direction, it has less space. Same amount as goes in, it goes out. We don't have accumulation, so it reduces the volume. So we are compressing the air. We inject it to the combustor. We can see that actually the air will go this way and then return. Here we have the combustion process, and finally we have part of the turbine. As we have described, the flow goes in this direction, and we have differences if it is a aircraft engine or is a power plant engine. Engine 2 have power generation. So, as we discussed earlier, we have the isentropic expansion. As we discussed earlier, we have the isentropic compression, isentropic expansion, and constant volume heat addition, which we have present in Rankine. So let's write this down. Okay, so we're going to analyze this cycle, and since this cycle is, as we mentioned, composed by 4 processes that involve mass flow through the boundaries, we cannot invoke first law for closed systems. We should invoke first law for open systems. So for open systems, we're going to have Q in minus Q out, and this is in rate form, plus work in minus work out, plus every component have just one inlet and one outlet. So we're going to invoke the mass flow rate that we have in the cycle, and H in minus H out equal the change in energy in the system with respect of time. One big consideration, a big assumption that we are making here is that we are kinetic and potential energy equal to 0. And this is not true when we are talking about aircraft engines, in which what we value is the velocity. So in that case, the velocity will be important, because that will give us a thrust for moving. So going back to the analysis, we can say that we are going to analyze first of all the compressor. So for the compressor, since it's an isentropic, we know that heat transfer is 0, and we are adding work. So then we will have work in plus mass flow rate times H1 minus H2 equal to the change in energy in the system with respect of time. So once it's in operation, and we should write it here as another assumption. That means it's a steady state. So we are making this equal to zero. So solving for work in, we're going to have mass flow rate H2 minus H1 If we divide by the mass flow rate, then we will have specific work in will be H2 minus H1. So this is for the compressor. If we follow the same procedure for each one of the components, we're going to get to these expressions, and you are asked to confirm them yourself. It's a way of practicing. Remember, we are going to start with this equation that is first law for open systems. If you don't remember well, chapter 4 is where you need to go. So once we do the analysis for the heat exchanger, we're going to have Q in equal H3 minus H2. For the turbine will be H3 minus H4, and all of this is in terms of specific energy. And in the second heat exchanger, we're going to have Q out H4 minus H1. The efficiency will be the same as every cycle that we have defined, what we would like to get, which is the net work, divided by what we need to give, is Q in. If we would like to give it in terms of enthalpies, will be H3 minus H4, that's the work of the turbine, minus H2 minus H1, that is the work of the pump of the compressor, divided by H3 minus H1, sorry, H2, which is the Q in. Since we are, if we try to look this on a PV diagram, we recognize that we have two pressures, right? It's 1, 2, 3, 4. So we're gonna, this ratio of P2 over P1, which will be the same as P3 over P4, we're gonna call it pressure ratio. It's not compression ratio, it's pressure ratio, because it involves pressures. So we can see that we have our same expressions here. We started with the first law. This is a simplified first law of thermodynamics. We can compute our Q in and Q out. Remember that for any given, let me go back a little bit, we're still having a heat engine, so we have high temperature, low temperature, the machine, heat in, heat out. So the first law. So we can change this by the difference. And once that we manipulate algebraically and recalling that this is the pressure ratio, we can get to this number. Again, this is valid only for constant specific heats. If you use variable, start from this and the properties from table A17. If we analyze this expression, we can see that again, the higher the pressure ratio, the higher the brayton efficiency, and we can recognize that in this graph. Another thing that we can see is that if we fix the temperatures, so if we are fixing this the maximum temperature and the minimum temperature, this can work, and this temperature will be the ambient, and this maximum temperature will be dictated by materials mainly. Then we're going to see that the pressure ratio will, at the beginning, if we have a very low pressure ratio, our area is small. As we increase the pressure ratio, the area which represents the network increases, and then if we keep increasing the pressure ratio, we're gonna decrease again. So the maximum for any two given pressure temperatures will be at this expression. Okay, as we mentioned, the highest temperature is limited by the maximum temperature that the plates can withstand, and also limits the pressure ratio that can be used in the cycle. As we mentioned before, the part of the work of the turbine is going back to the compressor, and we will call this the back work ratio. And this work ratio will be the work of the compressor divided by the work of the turbine, and it will be expressed in percentage. Let's see now a video of how the turbine engine will work. In this video, we're gonna watch the animation of how this engine behaves. It starts with drawing air to the compressor. You can see that in the compressor, as the flow goes by, as we mentioned, the size of the blades, or the space in between the blades and the shell, decreases, and that increases the pressure, reducing the volume. So we are compressing the air, and then we are gonna pass it through this chamber where it will mix with fuel. And usually you have this, the turbine and all the brayton engines. Here in this part, we're gonna inject. First of all, we make the air pass to this nozzle, so it will have this rotational movement that it will help to the mixing of air and fuel. And this line that you see in the back, we're gonna inject the fuel, and it's gonna be in jello in one moment. So this is how we have it, and we are injecting the fuel here, as you can see it, these lines. So once that we inject it in the center, and remember that we have this swirl of air inside, we're going to have a very good mixture. What we would like to have is a very good mixture of air and blue and fuel in jello. So once that we mix it, we pass it through the combustion chamber, and we're going to see that in just a moment. secondary. So we have more fuel here, and then we can see the burning of that fuel. The burning will create an expansion in the gases, and those gases will go to the turbine. This will be the high pressure turbine, and this will be the low pressure turbine. You typically have 4 stages, and this turbine is the one that will create the mechanical rotation of the shaft that at the end will be connected to a generator. In this case, the turbine is, and we have a turbine that we could go for a jet engine and turbine that will go for power generation. They have the same components, it's just that they focus on different things. A jet engine, you will worry about weight, efficiency, that will be a high pressure ratio, low NOx, this should be a capital O because it's oxide of nitrogen, low noise, the initial cost. And you will see that nowadays they are very focused on information that we can get from the turbine. Watch this video that will talk about the G and X aircraft turbine. Well, in power generation, you also get worried about pollution, but in this case, for pollution, we because they are in inland and they have different regulations, but they're very strict. Efficiency also, but what they focus more is on high temperatures because that will create a higher efficiency. Another thing is flexibility. Since these are used for power generation, these power plants need to go from zero to full operation in very small time. In this video, you will see that I can get it there up to 10 minutes. And flexibility is because they need to be adjusted for different loads. And serviceability, you want to have a very low downtime because that downtime is time that you are not making money. And same as in the jet engine, we are going to be focusing a lot on information because that information will allow for the user to get some important data that will allow them to predict when the service is necessary. So, some of the things that will make the part from ideal to the actual gas turbine, and you can imagine, is the compressor efficiency and the turbine efficiency. If you notice, this compression efficiency is exactly this turbine efficiency is defined exactly the same as in the ranking. So recall the ranking. This work is the actual work. This will be the isentropic work. For the compressor, resembles a lot of the pump work that we have, the pump efficiency that we have in Rankine cycle as well. The other two things that can help us to get a more actual cycle with the pressure drop during heat addition. That means that we have some pressure drop in the heat exchanger. Reasons for this variation will be reversibilities, pressure drops, and heat losses in any of these processes. As we already mentioned, these are the ways of improving efficiency, increase turbine temperatures. The design in the videos, you can see that the design of the blades are very important, and we are adding some modification to the basic cycle like intercooling, regeneration, recuperation, and reheating. These are similar to what we saw in Rankine cycle, so we are not going to study them for sake of time saving. Okay guys, following videos will be on solving some problems of these cycles. Thank you.